All right, ready to dive deep. Today we're tackling estuarine modeling. Want the inside track on this intricate world? You've come to the right place. We're breaking down an academic research paper, and trust me, it's way cooler than you might think.
What gets me is how much this field has exploded.
Mm.
It's like comparing an old hand crank calculator to, well, the device you're listening to us on right now.
Okay, before we get ahead of ourselves, picture this. A massive mixing bowl where the rush of freshwater rivers meets the salty expanse of the sea. That's an estuary. And they're absolutely teeming with life, from microscopic plankton to whales bigger than school buses. But with all that mixing and mingling, well, let's just say it's a challenge to study.
It's like, trying to predict the weather, right? But instead of a city, the city's underwater. And instead of buildings, you have, well, living, breathing organisms. Early scientists really had their work cut out for them.
But hold on, how did this all even start? Take us back to the early days of trying to model these watery wonderlands.
Picture the 1960s. The first estuarine models were surprisingly simple. Think one-dimensional. A single line attempting to capture the essence of a dynamic three-dimensional world. Computing power back then was a major, major limitation.
I can only imagine. Those old computers were the size of refrigerators, right?
Practically. But even those early models, they were groundbreaking. Take the work of Hansen and Rattray in 1965. They essentially laid the foundation for understanding how water and salt move in these complex systems.
Okay, so like a rough sketch that gets more detailed over time.
Exactly. As technology advanced, our models became more sophisticated. We went from those simple one-dimensional representations to two-dimensional models, kind of like looking at a map of the estuary's surface.
A bird's eye view. But we weren't done yet, were we?
Not even close. The real game changer. The leap to 3D. Imagine being able to actually see currents swirling around an underwater canyon, or how different layers of water mix and interact. That's the power of 3D. It allowed us to capture the vertical movement of water, essential for understanding how estuaries essentially breathe, exchanging oxygen and nutrients. And get this, 3D modeling revealed something totally unexpected.
Okay, I'm intrigued. Tell us more.
Well, it turns out there are these areas of upwelling, where nutrient-rich water from the depths gets pulled up to the surface. These are like hidden oases in the estuary, but 2D models completely miss them.
Wow. Talk about an aha moment. It makes you wonder what else we might be missing. We're basically trying to create a digital twin of one of nature's most complex creations.
It's an incredible challenge.
Right.
We've got the water itself down, but estuaries are teeming with life. That's where things get even more interesting and a whole lot more complicated.
Okay, so we got the water itself, but estuaries are jam-packed with life. How do you even begin to model something as wild and intricate as an estuarine food web?
That's where things get really interesting
Yeah.
and really challenging. We're not just simulating a few fish swimming around here. Imagine a complex network of interactions with creatures eating across different levels. It's a real-life game of who ate who with consequences for the entire ecosystem.
So it's like trying to model the entire stock market, but instead of companies, it's crabs and seaweed and everything in between.
Precisely. And each species has its own quirks and nuances. A tiny change in the behavior of one species, like a shift in migration patterns, can ripple through the entire system.
Talk about a butterfly effect. What happens if, say, a certain type of algae blooms earlier than usual?
It could cascade through the entire food web. Maybe the fish that usually feast on those algae aren't around yet, which could give another species a temporary advantage. Or it might even change the water chemistry, making it less hospitable for other organisms. It's all interconnected.
Okay, so how do you even begin to build a model that can handle that level of complexity?
That's the million-dollar question. We have to strike a delicate balance. Too simple, and we miss those crucial interactions. Too complex, and the model becomes unwieldy, even for today's powerful computers.
Finding that sweet spot is key. So we've got these separate models, one for the water itself and one for all the creatures living in it. How do we weave them together? That's where this whole coupling thing comes in, right?
Exactly. Imagine the difference between watching a pre-recorded nature documentary and live streaming a coral reef. Offline models are like the documentary you get a snapshot in time. But online models, especially those with feedback mechanisms, capture the dynamic interplay between the physical and biological elements. They're alive.
Okay, I love that analogy. So how does that actually work in practice? How do you get these models to talk to each other?
One common approach is to link the output of one model to the input of the other. For example, the water velocity output from the hydrodynamic model, how fast the water is moving in different areas, could be a direct input to the ecological model influencing how organisms drift and interact.
So it's not just about what each species is doing individually, but how the environment itself is shaping their behavior.
Exactly. It's like in real estate, a location is everything. The same species might thrive in one part of the estuary and struggle to survive in another, all because of subtle differences in water flow salinity or nutrient availability. And that's what coupling helps us capture.
It's amazing how much detail goes into these models. But how do we know if they're actually any good? We can't exactly strap on scuba gear and ask the fish for their opinion.
You'd be surprised what we can learn by observing those fish.
Right.
But you're right, we need rigorous ways to measure a model's accuracy. It's skill.
So how do you grade a computer model?
One common method is to compare the model's predictions to real-world data. It's a constant quest to minimize error, to fine-tune those predictions and make them as accurate as possible.
Like calibrating a high-tech instrument.
Exactly. But just like you wouldn't trust a single reading from even the most precise instrument, we don't just rely on the final outcome of a model run. We look at its performance over time, comparing it to data collected at various points. We're looking for consistency, of course, but we're also looking for those unexpected results. Because sometimes those outliers can reveal hidden flaws in our assumptions or highlight areas where we need more data.
That makes sense. It's like that saying, all models are wrong, but some are useful.
Precisely. We have to remember that models are tools, not crystal balls. They're based on our current understanding of the world, which is always evolving as we gather more data and refine our methods.
And that's what's so exciting about science. There's always more to learn, always room for improvement. So we've uncovered these fascinating insights about estuarine models, how they're built, how we measure their accuracy. But what does this all mean for the listener tuning in right now? Why should they care about this?
Estuaries are absolutely vital to our planet's health. They provide habitat for a staggering diversity of life. They filter pollutants, they protect coastlines from storms, and they support important industries like fishing and tourism.
They're like the unsung heroes of our coastal communities, working tirelessly behind the scenes.
That's a great way to put it. And by understanding how these complex systems work through tools like estuarine modeling, we can better protect them. These models can help us predict the impacts of pollution, climate change, habitat loss, and other threats. They can even help us design more effective strategies to restore damaged ecosystems.
So it's about more than just equations and algorithms. It's about using those tools to make informed decisions to protect these incredible natural resources for future generations.
Absolutely. And that brings us to a final thought-provoking question for you, our listener. What role will you play in the story of our estuaries? Will you become a citizen scientist contributing to the data that fuels these models? Perhaps you'll be an advocate pushing for policies that protect these vital ecosystems. Or maybe you'll simply share what you've learned with others, spreading awareness about the importance of estuaries and the incredible science dedicated to understanding them.
Every action, big or small, ripples outward. This deep dive has given you a taste of the fascinating world of estuarine modeling, a world where science and technology converge to help us understand and protect these irreplaceable ecosystems. If you're eager to dive even deeper, we encourage you to check out the full research paper. The link is in the show notes. Until next time, keep exploring, keep asking questions, and keep those brains engaged.